Welcome students. We are ready with the new module of the Hypersonic Aerodynamics. We are in the wake of studying the local inclination method, in which we are just trying to find out different methods in which the local inclination is involved, and this local inclination itself is enough to give the idea of the pressure distribution. These methods are not very accurate, but they give very much agreeing kind of result, and they have their own reasons for this, although they normally don't deal much with the free stream Mach number. Mach number becomes almost ignorant, but still they are able to predict good result which are very much matching with the experimental results and the exact results as well. The reasons are different for different methods, and we have already seen one such method, something called Newtonian flow theory, Newtonian flow methods, or Newtonian sine squared law, in which we know that why it is very much close to the hypersonic flow regime and giving the ideas about the correct values, but it doesn't make much sense. Still it is matching. Now we are going to study a different method today, that is tangent wedge and tangent cone method. This method is also as usual as the previous method, includes the local inclination and gives the idea about the various quantities in the hypersonic flow over the surface. When saying various quantity, what we mean is actually the pressure, especially the pressure, and once you know the pressure, you can find the coefficient of lift as well as coefficient of drag, and then L by D ratio as well. Pressure in some way is also related with the velocity through the Euler equation and the Bernoulli equation. So some idea will be given towards the velocity also, but mostly we are concerned with the pressure. So let us just deal and go a little bit deeper into the tangent bend method and see how it actually is applicable in the case of hypersonic flow regime. Here is a simple case in which a body is being shown which is facing a hypersonic flow, and we have chosen a point I on the surface, this point I on the surface, and we are trying to analyze the pressure on this point I and try to see that how the tangent wedge method is applicable to find the local surface pressure here. Here this body is having a deflection, local deflection theta I, but this theta I is not constant, actually it's varying throughout. So as we go along the axis of the body, this is the actual body, the deflection of the flow which is actually meeting the surface of the body will keep varying. This is not constant. Now let us believe and let us just assume that at the point I, the local surface deflection is actually theta I. So theta I will be the angle between the free stream velocity, the free stream flow, and the tangent at this particular location, particular point. Now our job and the motive is to find the pressure at I. Let us say let's call it Pi, and only thing given is the theta I, the deflection. So now we are going to assume a super assumption, something very funny and look like it not make much sense, but it is giving a very close result. We'll just discuss also why it gives the close result. So let us assume an assumption that the pressure at location I, this location I, due to the local inclination theta I, is equal to the pressure available on the wedge of half angle equal to theta I. Now we just trying to assume that there is a wedge available here. It's a imaginary wedge, and this wedge is having half angle equal to theta I, the local deflection available here. So for this particular location we get one wedge, And since this theta I deflection is varying throughout, we just know that the for different location we'll get a different wedge with a different half angle. For this particular location we have got one wedge with a half angle theta I. This theta I, if facing the hypersonic flow like this, will create a shock like this. So we have a wedge shock. The actual body is like this, and actual body is creating a shock which we are calling it a body shock, which is actually a somewhat like a bow shock, but this is not a detached shock. So we have to actually mind here that this method is not applicable in the case of detached shocks. So this cone angle, the leading edge angle must be lower than the maximum angle for the detachment of the shock. So if this angle is large enough, then for the particular Mach number, the shock will get detached. And in that case, we will not be able to use this tangent cone and tangent wedge method. So for this method to be applicable, this angle at the leading edge must be lower than or below the angle, the maximum angle for detachment. Actually this is a minimum angle for detachment, and in that case we will like to have a attached shock, though it's a bow shock. The bow shock is because the strength of at the leading edge at this location is almost equal to normal shock, then the strength keeps coming down. So bow shock is actually a combination of different shocks starting from normal shock to Mach wave, depending upon the strength. And then this shock remains attached. So we assume that one wedge is available here. This body is not available, one wedge is available. So this wedge is actually having a half angle equal to this deflection angle. So in that case the flow will actually have the similar effect. So at this point the flow is getting deflected by theta I. So when the flow comes, even in this absence of this body, if the only wedge is available, the flow will get deflected by the same angle. That's the common point we are having between these two assumptions. Actual body is there, so we replace this body by a wedge of similar angle actually here. This wedge will create a shock, imaginary shock. We are calling it wedge shock. So now we have two shocks, body shock and the wedge shock. And we assume according to this method that whatever the pressure would be there because of this shock available, and this shock is being generated because of this imaginary or what you call equivalent wedge. So whatever the pressure is available at this location on the wedge, because of availability of this wedge shock, the same pressure will be available at this location. Hence the wedge is not there and the actual body is there. This also looking a little bit logical and looks like it's actually the correct assumption. It's actually the correct method and the correct value, but actually it's the assumed value and the approximate value. They will not be exactly same. And where these two concepts are differing, the one concept that actual body and this bow shock, and second concept that's imaginary equivalent wedge and this wedge shock, these two concepts are differing in one point, that this pressure at this point the deflection is actually a gradual. The flow first comes here and a deflection is given to this abruptly, then this deflection keeps going down, and finally this deflection is available after a gradual change in the deflection starting from this leading edge. But if we have a wedge here, this wedge will actually give an abrupt change, and abruptly the flow will be deflected by this particular angle. So these two effects thou will be very similar and will give a very much similar effect. Still they will be much different, and then this difference will actually make our value a approximate value. This will not be exact value. Now if we can assume that both the situations are same, whether the change is abrupt or gradual, if these two are very close and almost same to each other, then the pressure available and this particular location in the case of wedge will be exactly same to the pressure available in the case of actual body. That's the concept we normally follow in the case of a tangent wedge method. So we just find a tangent and then we assume this tangent to be a wedge, and then we find the shock available, and then we actually find the pressure here. This we can actually find a different location, so we can, after that we can plot it, and then we will get the exact the total pressure distribution over the surface. If you can find a relation, then actually the relation in this the surface of the body, then we can actually use the computer programming also, and we can have a very large number of the points available on the surface, and then a real good idea about the surface pressure distribution can be found. Once we know the deflection angle, then it becomes easy, because all these we are studying the deflection angle methods. One method we have already studied, that Newtonian flow method or Newtonian sine squared law method. Now with the second, in the tangent wedge method, we proceed as the moment we get the deflection method, first thing we do is that we create a wedge, a imaginary wedge of the same semi angle actually, and then this becomes the deflection angle. So once you know the deflection angle, then we find the wave angle corresponding to the deflection angle of the surface. So we got the wave angle now. So we have got the wave available, and we have got deflection theta available. So it means theta and beta both are available for us. Now if you have the theta and beta from the shock table or the shock relation, we can find the pressure. So method is very simple. It's just straightforward. Only thing we have to understand here is that depending upon the deflection, we are replacing the body by a wedge, and this wedge will be different at different locations. So number of wedge we'll have to assume will be equal to the number of points we need, and if you have this infinite number of points, we need infinite number of wedge. So computer programming will be required for this. Otherwise we can have discrete values, and we can do that. We can do the hand calculation also. This is very simple to understand actually. Now suppose this is what we saw actually, the 2D case was there. Now suppose there is a 3D case, an axis symmetric body is available. In this case we just don't have to differ much actually. Instead of tangent wedge method, what we follow here is called tangent cone method, and this is not much different from the earlier method what we said, the tangent wedge method. Instead of assuming the imaginary body to be a wedge, we assume it to be a cone, and then the rest of the thing follow as it is. In the we assume a cone which is actually with slant surface is making a tangent at the point under consideration here. So this is the point I. So this cone should be actually exactly tangent at this location, and in that case this is a deflection angle. So when the flow comes here, it becomes parallel to the surface. So then the deflection angle will be theta I. I is the location. So this theta I should be equal to the semi angle of the cone. Like we have the semi angle in the case of wedge, the semi angle in the case of cone. This semi angle, this cone will actually give a conical shock, a cone shock. 3D shock will be available, and then we have the body shock here. So again we have two situations available: the actual body and the body shock, and other situation is a cone, a corresponding or equivalent cone with a cone shock. And it's again not to be forget that this cone will actually vary for different location. It depends upon the location to location. In both the cases, we just solve the shock relations, and then we find the pressure inside it. Here you have to be we can just understand it, and we should not notice it that when we have a cone here and then we have a shock here, the pressure throughout in this region entire, we can call it actually the thin shock, the shock layer, and it becomes a very thin in the case of hypersonic flow. So in this region the pressure remains same throughout, because the pressure change is taking place exactly at the point when the shock meets the flow, and after the flow, the shock after the shock, the flow becomes actually isentropic. Only the shock is the isentropic phenomena. After that becomes isentropic, and throughout the pressure remains same. But in the case of actual body and the body shock available, there is a small problem here. It doesn't always remain same. So we have a different values here that we are going to analyze and see how it's happening actually. Now, first of all, before we actually go into that thing, that what happens, let us just try to see that what is the logical deduction and the logical understanding which is actually trying to make us believe that the pressure on the surface of a body is exactly equal to the pressure on the surface of a cone or the wedge, as per the case may be, provided this deflection angle at the particular location is exactly equal to the half cone angle or the half wedge angle, depending upon the axisymmetric and the two-dimensional body. Let us consider on the same picture again, where we have a two-dimensional body here, and that at the point I we have a deflection theta here, theta I, because this theta I is making an angle. The tangent at this I is making an angle theta I with the horizontal direction, which is actually also the direction of the that uniform flow. Now we draw a normal at the point I. So there is a normal on the surface at the point I, which is actually going like this, and it's actually meeting the body shock like this here. The broken line gives the imaginary weight surface. This is a broken line here. This broken line is actually the imaginary weight surface, and dashed line represents the imaginary oblique shock. This is the dashed line. So it's imaginary oblique shock or the weight shock, whatever we call it. Now the perpendicular drawn on the surface crosses the imaginary shock below the actual shock in the flow. So this line, when it is drawn, it's perpendicular to the surface. Remember, this is perpendicular to the surface, not perpendicular to the this shock, body shock, neither the weight shock. It's perpendicular to the surface at this particular location, and this is going directly up, or just perpendicular. So it is meeting these two shocks here, and it is always looking like it's actually meeting this shock below the body shock. Now let this body shock cuts the perpendicular cuts the body shock at point A and the imaginary shock at point B. So we have 3 points, I, A and B. We can just see this thing in the exaggerated picture. This is the exaggerated picture of this particular location. This is your I, the location here, and then we have, this is the portion of the equivalent wedge, and then this is the wedge shock, and this is the body shock. So this is the perpendicular goes directly from the I, and it cuts the two shocks at B and at A. Now having well aware about this situation, we just try to state a fact, which is fact actually, but we'll just see this later. Let me make the statement of the fact that in the hypersonic flow across the oblique shock wave on the cylinder body, the y component of the velocity v is changed much more strongly than the x component. Let me read it again for you. In the hypersonic flow across the oblique shock wave on the cylinder body, the y component of the velocity v is changed much more strongly than the x component u. What does it mean actually? Now suppose we have this this value here. Now the flow is coming directly like this. So the change in the velocity at this location, the velocity will be actually parallel. One velocity will be parallel to the surface, other will be normal to the surface. So parallel to the surface velocity change will be actually we have this m1 or something like free stream velocity, or you can say that that upstream velocity. The downstream velocity, after the changes have been made here at this particular location, we can get u and u2 and the v2. Now u2 is along the surface. That's what is actually mean. We are resolving the flow along the flow and perpendicular to the flow. So the changes in the along the surface will be actually smaller compared to the changes in the normal direction. That's what it means actually. So in the hypersonic flow across the oblique shock wave on the cylinder body, the y component of the velocity v is changed much more strongly than the x component. Let us just see how it actually happens. This is the normal case of a shock, and this is the wave angle, and the flow is coming like this thing. So flow is actually, now after this the flow becomes v2. It gets deflected. So this v2, the flow after the shock, because after the afterstream or something like downstream flow of velocity is resolved in two components, one along the flow and other perpendicular to the flow. We have v2 u2 and v2. Now in this case we have this relation available to us, and this relation, this v2 u2 by v1 and v2 by v1, which we have dealt already in different sections. So we'll take just start from here and try to see whether our statement we made just now is actually correct or not. So we know this v2 and v1 relations, u2 and v2 relations. Now these values are exact values. We have not made any kind of assumption here. So now let us make the assumption. Once you make the assumption, then find that this u by v1 is delta u. Try to understand this, delta u, because if you take the whole thing that side and this factor this side, it become 1 minus v2 by v1. So in that case, v2 u2 is the total velocity. It's a total velocity in the x direction or in this particular direction. So the change in velocity is u2 minus v1. So if you take this to this side and this whole thing goes the other side, becomes 1 minus u2 by v1. So actually it will give you u2 minus v1, that is delta u, the change in this particular direction. Change in we are taking it, you can say it x direction. So change in u in the x direction, velocity in x direction, divided by the actual velocity. The actual velocity was actually v1. And similarly, this also can be taken as there was no velocity in this particular direction. Try to understand here. Initially there was no velocity perpendicular to the v1. So whatever has come after the shock, after the after crossing the shock, that is a change. So this v2 itself is a change here, and in this case change will be actually 1 minus u2 by u1. So these relations are also very perfect. They are meeting our mathematical requirements. Now after this, when we apply the hypersonic assumptions, then we get this value here. Sorry, let me see this thing. We get that gamma plus 1 by 2 into actually that theta square. So we saw that this the order of the this is the delta u by v1, and delta v will get theta, just theta. Just apply this thing, and you just have a small practice, and that you see that actually after putting this limit that m1 tends to that infinity, will actually get these values here. Theta is just a theta here. Sin theta become theta and all those things, and theta and this one more, theta is coming through the theta beta relations. Theta beta relations all again in the case of hypersonic assumptions. So that we have already seen in the hypersonic assumption that actually for the gamma is equal to 1.2, the theta beta becomes 1.2 times of theta. The same relation, that theta is equal to gamma plus 1 by 2. I think that's the one, and gamma plus 1 by 2 into beta is equal to gamma plus 1 by theta. So just replace beta by theta. So these things will come into picture. Now by looking at this, it becomes very evident that the change in u is actually of the order of theta square, and change in v is of the order of theta only. So theta already is in the radian, so it's very, very small. So squaring a small quantity will become further small if it is less than 1. So the statement we made earlier, that in the hypersonic flow across the oblique shock wave on the cylinder body, the y component of the velocity v is changed much more strongly than the x component velocity u. So we can see that the y component is changing at 1 degree higher than the x component. That's what it means actually. Now let us see how it is useful in understanding our logical deduction. Now let us just go to this thing again. This is the picture we have in this thing. This is the exaggerated picture at the exact location of our point under consideration, and then this angle, this normal is cutting to both the shocks, and then we are getting all the situation like this. Now we apply the Euler equation here. We already know that velocity change across this normal direction is more severe than across this along the tangent direction. So not only velocity is also related to the pressure through the Euler equation. So if the velocity change is high, there is going to be a high change in pressure as well. Of course, it will be of the negative direction. It means the velocity increases, the pressure will come down. That's what it actually means. Now, keeping this in mind, we find that the PI, the pressure at the I location, is actually smaller than the pressure at the A location. In the normal cases, what happens is, if suppose there is a simple wave available here, just it's not a bow shock, just a simple wave available. In that case, whatever the pressure is available here, this pressure comes after the changing through the shock. The same pressure should apply throughout in this particular region. It means the same pressure should actually act on the surface as well. But due to some reason, they are changing, and the reason is centrifugal force. They are not same. Some pressure is coming here because of the shock. That's a high pressure available here. Now at this location, since the theta is changing, the body surface is having a curvature. So the flow which is coming here is actually getting a circular motion, and when the circular motion is coming, it gives a centrifugal force. So because centrifugal force, the pressure which would have been exerted on this particular location after the pressure from here will be little smaller. So the shock is trying to impress its pressure just behind it, that is PA, is just trying to impress it on the surface and making it PA is equal to PI. But because of this circular motion here, a centrifugal force is coming to picture, and that will actually reduce the pressure a little bit. So PI is smaller than PA. That's what happened in the one scenario, that we have body, the actual body, and we have a body shock. Now at this location, if you talk about the PB, the pressure at the B is actually again smaller than PA. Why? Because when this normal cuts both of these, then the local wave angle will be having a relation that the wave angle of the body shock is actually larger than the wave angle of the wedge. So a larger body shock wave angle will actually give a higher pressure. So at this location, we have a pressure lower than this. So we can see that the pressure is lower than PA in both the cases. Both are this thing. And what we have actually assumed in our tangent wave, or the tangent wedge method, is that PB is equal to PI. If you remember this, we assumed that whatever the P is coming here at this point, because this particular wedge shock, we are getting some kind of pressure here. The same pressure we assume equal to be here. That's the application and the working out of the tangent wedge method. So both the pressure PI and PB are less than the pressure behind the shock, that is actually PA, and this is because of two different reasons. The PI is lesser than PA because centrifugal force, and PB is lesser than PA because of the wave angles, different wave angles. But they both are lower and they both are smaller, and they are not differing much actually, and it looks like they are smaller by the same reason. So it is actually reasonable approximation for the pressure PI, that we can actually take that PI is equal to PA. It's just a logical deduction. We don't have any equations which can actually derive. So logically we assume. And why we actually trying to assume this and try to prove this logically? Because practically it has been found that despite this method has got no logical and no conceptual derivation, there is no analytical derivation why we should assume that that at this particular location whatever the slope is there, and assume a wedge, and that wedge whatever the pressure comes here because of because the wedge shock is equal to the same phase. There is no logical actually understanding. There is no logical comprehensive idea is coming here. But despite all this, still it is able to give a very close result. A problem solved using tangent wave method or tangent wedge or tangent cone method is actually matching the actually found value in a very close manner, whether it's exact value or it is actually the experimental value. This is actually matching. So that's why we try to prove it, that what would be wrong, what would be the actually the reason behind this. So reason is actually both these values actually falling in that below this PA, and they are supposed to be very close to each other. So assuming PB is equal to PI is a reasonably logical concept, despite there is no analytical proof for this. So that's what is total about this tangent wave and tangent cone method. And also we can see that that is in the case of a body, a 3D body or axisymmetric body, instead of just taking the wedge, we can take the cone, and the similar concept applies there. So we can actually use the cone pressure in the case of axisymmetric body. Now let us take a sample case and just see what happens there. So we have a simple ogive available here. This ogive is actually facing a Mach number, which is hypersonic Mach number, and this is actually D by L is a slenderness ratio. This is D and this is L. So and this D by L, it also, if suppose this is a straight line, then it will be something equal to tan theta, 10 of the half of angle. So basically this is actually a theta, and theta is nothing but the deflection. So a deflection, theta deflection, both joining together something like Mach number and the theta or the deflection both joining together, again it becomes a hypersonic similarity parameter. If you all can recall what we have studied long back, same thing is coming here. So this is a parameter, md by L is nothing but hypersonic similarity parameter. So for various values of hypersonic similarity parameter, the pressure ratio has been actually calculated throughout the length, and then it will be plotted. So this tangent cone method has given this dotted line using tangent cone method. So tangent cone method it means this body has been taken as the axisymmetric body, something like a bullet is facing a very high speed flow, supersonic or maybe in the hypersonic regime. So these dotted lines are actually plotted for the tangent cone method, and then using the method of characteristics, they have found the actual values here. So this is actual method of characteristics is actually a very close result, and we call it exact. Though it's not experimental result, but we call it exact. Analytically, this is the best result we can find. So the exact result is very much matching with the tangent cone method. So it's actually reasonably good enough to actually, when you design any hypersonic vehicle, we can actually use the tangent cone method. We see that it's very much matching actually in all the cases, and something like 2.29 is matching too much like this thing. At 1.0 of the hypersonic similarity parameter value is actually differing little bit here. This is not matching, not giving a very close result, but for other values it is very close result, and we actually use this in while designing it for the conceptual design. Now that's all for the case of tangent wedge and tangent cone method. Next session we'll have this approximate method, and that's again a inclination method. We are still there are 3 inclination method we have to study as per your syllabus. Then we'll go for the other methods. So till we meet for the next video session, I wish you all the best. Thank you.